Alright, well, I'm going to give it a go here, see how it goes. I wanted to share with you the basics of differential calculus. You know, definition, then linearity, and hopefully power rule, those things. Essentially sections 3.1, 3.2, 3.3, and 3.4 in my notes, which is what we have in front of us here. Now, my printer, a little bit sketchy, but not nearly as sketchy as my handwriting today. Check this out. Excuse me. So, just to remind you, the definition of the derivative, if this limit difference quotient exists, right, then we say f is differentiable at a, and we say f prime of a is the derivative, and we say the function has slope f prime of a at a, and also the equation of the tangent line is f of a plus f prime of a times x minus a, if that limit exists, right? So, anyway, as I point out here, it's also useful to make the substitution x equals to a plus h, and so you can trade the limit in h for a limit in x going to a instead. That sometimes makes it easier. The average velocity, if you look at that and take the limit as the delta t goes to 0, that's how you get instantaneous velocity, basically right here. All right. So of course this is one of the fundamental motivating problems for calculus, was Newton and wanted to do infinitesimal calculus. All right. But just to be clear, in Newton's time, in Leibniz's time, they didn't really do limits, and they took a sort of more freewheeling, kind of sketchy way to do calculus, I suppose. But they were very smart, so it worked out. Anyway, so moving along here. Actually, Newton used to think about calculus in terms of these things called fluxions. Some sort of very, very small thing that wasn't zero, but was very close to zero. And it's an interesting story, the story of fluxions, and ultimately it gives birth to so-called non-standard analysis, which is an alternative way to do calculus without limits. But anyway, enough about that. That's not what we're doing. Here we go. In-class example. This is what I wanted to get to. Excuse me. It's safe. This is video. Find the slope of the function y equals x squared at x equals to 1 and graph both the function and its tangent line. Alright, so we have f of x equal to x squared. So f prime of 1 would be limit I'm going to use the x formulation this time. X goes to 1 of f of x minus f of 1 divided by x minus 1. Alright? Now, that is the limit as x goes to 1 of x squared, because f of x is x squared. F of 1 squared is 1, minus 1, over x minus 1. Of course we have an indeterminate type, 0 over 0. And so this is limit x goes to 1 x plus 1 times x minus 1 over x minus 1. So, thankfully, these guys, we're just left with x plus 1. Plug in the limit point, what you get? 1 plus 1, also known as 2. Alright, so the slope of y equals x squared, x equals to 1 is 2. That makes a lot of sense. Y equals x squared. Looks like this, right? And if we're at x equals to 1, wait a minute. Yeah. Well, anyway, wherever 1 is here. Right. Suppose it's here. Then the tangent line is going to be something like that, right? And the equation for the tangent line, y is equal to f of 1 plus f prime of 1 times x minus 1. Sorry, my handwriting is so horrible. It's hideous. Hideous, I tell you. 1 plus 2, I just calculated f prime of 1 is 2, times x minus 1. But of course that's 2x minus 1. So that's the equation of the tangent line. As you can see, it's got a y-intercept down there. Like that. Alright, so there we go. Now, before you know it, we'll have a slightly easier way to calculate derivatives. But for the moment, we're calculating derivatives from the definition, okay? Now, this next example I think we discussed in the lab a little bit. In fact, with this previous example I might have done in the lab. I feel like that might have been in the lab. I don't know, it seems like forever ago. I've done nothing but sleep since that lab, but, well, and cough. Lots of coughing. Nothing but coughing. Anyway, let's see here. Absolute value. Yes, so the absolute value function does not have a derivative at 0 because the left and the right limits don't match. So, all right. Another example. Let's see here. The graph of y equals the cube root of x is a vertical tangent at 0, 0. Let's see here just to show you that. Y equals the cube root of x. This is the graph of y equals cube root x. As you can see, there's that place right there at 0. It's got a vertical tangent line, which suggests that the derivative of this function, right, is going to be undefined. Well, really, it's going to blow up at a 0 to be infinity. Let's work it out. So f prime of 0. So to the limit as h goes to 0 of the cube root, I guess I'm calling this f of x, by the way, cube root of 0 plus h, right? Minus the cube root of 0 divided by h. Alright. That's the limit as h goes to 0. I have never been more disappointed with my handwriting, I tell you what. Anyway, so that's the cube root of h divided by h. So you've got 1 over h to the 2/3 power, actually. And 1 over h to the 2/3 as h goes to 0. We've got 1 over something really, really small and positive. So this, my friends, is in fact infinity. Yeah. And I would have sent you the video from last year where I did this, but sadly when I made that video, I didn't pan the camera for like 10 minutes in the middle of the video, so it prevented me from using it. So you're getting this very high quality, low energy, mostly cough-free video instead. Haha. Haha. Alright, let's see. So functions can fail to have derivatives at a point because they could have a kink in the graph, they could have a vertical tangent, they could also have a place where they're not continuous. Here's a theorem. Excuse me. Excuse me. Excuse me. If f is differentiable at a, then f is continuous at a. Alright. Oh. Good news, I'm not proving it right now. I would defer the proof until the end of this section. I feel like I might ask you to prove this in homework. I'll try to keep that in mind. I do mean to prove this for you. In-class example. Identify the points in the given graph for which f prime of a does not exist. Well, I guess it's time for me to make up an example. Alright, I guess that's good enough. So this one, I'll circle the treble points. So this point right here is a treble because we're going, there's a corner in the graph, right? So that's going to have there's no well-defined tangent line right there. The derivative's not going to exist. I think right here we're also going to have a problem. So here we're going to have f prime does not exist. Here we're going to have f prime is infinity, but still does not exist. That's just a different kind of not exist. Right here doesn't, derivative does not exist. It's a kink in the graph. And, yeah. So that's pretty much, you got to look out for kinks or corners in the graph and vertical tangents. There are other ways the derivative may fail to exist, but that's a good couple things to get us started. Yay, more examples. Okay. I have f of x is 3. Calculate f prime of a. F prime of a equals to limit h goes to 0 of f of a plus h minus f of a divided by h. But f of x is 3. So that is the limit as h goes to 0 of 3 minus 3 over h, also known as 0. So f prime of a is 0. The derivative of a constant function is 0. That makes sense, right? Constants don't change. How about this one? F of x equals to mx plus b. Calculate f prime of a. Alright, let us do it. f prime of a equals limit h goes to 0 f of a plus h minus f of a divided by h. I'm making myself write out that step so that I don't get lost. Limit h goes to 0 of m times a plus h plus b minus, parentheses are your friends, m a plus b divided by h. Okay, so these b's cancel, right? And this ma and that ma cancel. We're just left with mh over h. Limit h goes to 0 of mh over h. Of course the h's then cancel and we're just getting m. Well, this makes sense. Certainly the slope of a linear function should be the slope of the line y equals mx plus b, right? Excuse me. Here we have f of x, x cubed plus x minus 2. Calculate f prime of 2. F prime of 2 is the limit. I'm going to use the x formulation this time. X goes to 2 of f of x minus f of 2 divided by x minus 2. Alright. Again, my apologies for this horrendous handwriting. X goes to 2. So I've got x cubed plus x minus 2. Now f of 2, I'll calculate over here. F of 2, 2 cubed plus 2 minus 2, so it's 8. Alright. Now, something beautiful is going to happen in all these kind of problems. There's going to be a factoring. And the factoring is, it's not going to come from nowhere. It's going to come from the denominator. Like it's going to be reflected in the denominator. So check it out. Limit x goes to 2, x cubed plus x minus 10 divided by x minus 2. Alright. You're like, well, you didn't do anything. That's true, I didn't, not yet. So, if you plug in 2 into the numerator, you get 8 plus 2 is 10. 10 minus 10, 0. So by the factor theorem, x minus 2 is a factor of the numerator polynomial. So we can factor out x minus 2 from that. So with these derivative problems, the factoring like always works out. Alright, x minus 2 x squared plus 2x plus 5 divided by x minus 2. So you see those cancel, and then we can plug in 2 to get the slope here, right? Two squared plus 2 times 2 plus 5, 4, 8, 13. So there you go. Excuse me. Now this here business on Carathéodory's characterization of differentiability, I will come back to when and if I am well and in class, because we can come back to this. Don't worry about it for now. Alright, that said, I should probably, that's probably where I was, that's the proof of differentiable implies continuous. I usually use Carathéodory's theorem. So let me show you a different proof right here. So, alright, so differentiable implies continuous. See if I can find here, I'll write on the back of this page. Here we go. So, proof. Suppose f prime of A exists. Consider limit as h goes to 0 of h times the limit as h goes to 0 of f of a plus h minus f of a divided by h well, this is f prime of a, right? So that exists. And this works out to be 0. So we know that this is all equal to 0, right? But by the properties, the limit product of the limits rule, we also can rewrite this as the limit as h goes to 0 of h times f of a plus h minus f of a divided by h. So the h's cancel, and that gives you that the limit as h goes to 0 of f of a plus h minus f of a is equal to 0, which tells you that the limit as h goes to 0 of f of a plus h is equal to f of a. And that is continuity of f at a. So that's a proof that differentiable at a point implies continuous at a point. So if you have a function which is not continuous, it's also not going to be differentiable. All right. Now, just because a function is continuous, that doesn't mean it's necessarily differentiable either. But at a bare minimum, it has to be continuous. All right. I'm going to stop here and start again.